5 million years ago, a creature walked through the ancient woodlands of East Africa. Not quite ape, not quite human. Something in between. A missing link in our evolutionary chain that carried the first sparks of what would become human instinct. Imagine standing in that primeval landscape, the air rich with scents unknown to modern noses, the ground beneath your feet untouched by civilization. This was a world of predators and prey, where survival depended on something more than just physical strength. It required something that would eventually define humanity, instinct refined into intuition, the ability to predict, to anticipate, to understand without knowing why. This invisible force has guided our species from those distant forests to the stars. But how did this begin? When did we first develop the capacity to sense danger before it struck? To communicate without words? To create social bonds that would eventually build civilizations? The answers lie buried in a time almost beyond comprehension. 5 million years, a number so vast it defies easy understanding. 200,000 generations of beings that led to you, each passing along not just genes, but something more elusive, the instinctual blueprints that still operate in your mind today. Tonight we journey to find these origins. We'll excavate the cognitive foundations that made us human. This is not just a story of bones and tools. It's the story of consciousness itself, how a specific type of awareness emerged from the primordial world. The evidence exists in fragments, scattered across disciplines from paleontology to neuroscience, in the fossil record, and in your own reactions, in the ancient stone tools, and in the way your heart races when you sense a shadow moving in the dark. Scientists have long debated when our uniquely human qualities first appeared. Some place it with the emergence of sophisticated tools, others with the control of fire, still others with the development of complex language. But what if these were merely expressions of something deeper? What if the essence of humanity, our instinctual architecture, began far earlier? What if the foundations were laid 5 million years ago, when our ancestors first left the dense forests for the mixed woodlands and emerging savannas of East Africa? This transition represents one of the most significant environmental shifts any species has ever faced, from the relative safety of trees to the dangerous open spaces where predators roamed. A change that would have demanded new ways of thinking, perceiving, and reacting. Tonight's exploration takes us to this pivotal moment. We'll examine how environmental pressures may have selected for the first glimmers of human-like instinct, how the need to detect threats, find food, and form protective social groups rewired primitive brains. Fossil evidence gives us the physical changes, gradually lengthening legs, shifting spine, changing hands. But what of the neural adaptations that left no direct physical record? How do we find evidence for the birth of instinct? The answer lies in a multidisciplinary approach. By combining fossil evidence with primate studies, anthropological insights with neurological research, evolutionary psychology with careful observation of our own instinctual responses, we can reconstruct this lost chapter of our story. You carry within you the legacy of these ancient adaptations. When you intuitively read someone's facial expressions, when you unconsciously detect a threat before conscious awareness, when you feel drawn to certain landscapes without knowing why. These are echoes from 5 million years ago. We'll start with what we know for certain. 5 to 7 million years ago, the lineages that would become humans and chimpanzees diverged. This is supported by genetic evidence, with humans and chimps sharing approximately 98.8% of their DNA. The earliest potential human ancestors from this period, creatures like Sahelanthropus chadensis, Aurorintuganensis, and Ardipithecus, show the first signs of adaptations for upright walking. A momentous shift that would free hands for tools and change everything. But bipedalism itself isn't what makes us human. Birds walk on 2 legs. What makes us unique is the suite of cognitive adaptations that would eventually follow. The question is, when did these begin? And what triggered them? Some researchers believe our cognitive evolution accelerated during climate fluctuations that transformed East African forests into mixed woodland savanna environments, creating selective pressures for enhanced situational awareness social coordination, and predictive thinking. Surviving in these new, more exposed environments would have required heightened vigilance. The ability to quickly detect predators, to communicate danger silently, to read subtle environmental cues, the foundations of what we now call intuition. This is where our story truly begins, not with fully formed human minds, but with the first neural adaptations that would eventually bloom into human consciousness. The dawn of our uniquely human instincts, emerging from a time of profound evolutionary pressure. As we explore this ancient world tonight, we'll search for evidence of these earliest cognitive adaptations. We'll examine how they might have manifested, how they shaped subsequent human evolution, and how they continue to influence your thoughts and behaviors today. The journey will take us across millions of years. Through changing landscapes and evolutionary milestones, we'll meet our distant ancestors and the challenges they faced. We'll see how each adaptation built upon the last, creating the complex instinctual architecture you've inherited. This is your origin story, the beginning of human instinct. A tale written not just in bones and stones, but in the very structure of your mind. So settle in as we travel back 5 million years to witness the dawn of what would become humanity. Chapter 2. Premise and stakes. Why does this matter? Why should we care about instincts that emerged millions of years before recorded history? Because understanding the origins of human instinct changes everything. How we see ourselves, our behaviors, and our future as a species. These ancient adaptations aren't just historical curiosities. They actively shape your daily life. They influence who you find attractive, how you respond to stress, your social hierarchies, your fears and desire, even your political inclinations. Consider your inexplicable fear of snakes, even if you've never been harmed by one, or how babies instinctively grasp with tiny hands, or how you can sense when someone is staring at you. These aren't learned behaviors, they're evolutionary inheritance. The stakes of our exploration are profound. If we can identify when and why our distinctly human instincts first emerged, we gain insight into the most fundamental question of all: what makes us human in the first place? The traditional view of human evolution focuses on physical changes, bipedalism, brain size, tool use. But these are just the visible expressions of deeper cognitive adaptations that began much earlier. Adaptations that truly set us apart as a species. What if our most human qualities, our capacity for empathy, complex social organization, creative problem solving, and abstract thinking, aren't recent developments at all? What if their foundations were laid 5 million years ago in those first pre-human minds? This would fundamentally alter our understanding of our evolutionary timeline. It would suggest that what we consider uniquely human isn't the result of a recent cognitive revolution, but rather the culmination of adaptations that began with our earliest ancestors. The implications extend beyond academic interest. Understanding the deep roots of human instinct could transform how we approach everything from education to mental health, from social policy to technology design, from environmental conservation to space exploration. Consider how we structure our societies. We create environments radically different from those we evolved in. Cities of concrete and glass, digital interfaces, artificial lighting, processed foods, all while carrying instincts calibrated for a world of natural threats and resources. This mismatch between ancient instincts and modern environments may explain many contemporary challenges. Rising anxiety and depression, political polarization, addictive behaviors, even our difficulty responding to long-term threats like climate change. Our brains evolved to respond to immediate dangers, the rustling in the grass that might be a predator, not abstract threats that unfold over decades. We're running Paleolithic hardware on civilization's software, creating inevitable system conflicts. But if we understand the original purpose and context of these instincts, we gain the power to work with them rather than against them, to create environments and institutions that align with our evolutionary psychology rather than contradict it. For instance, our instinctive preference for immediate rewards over delayed gratification made sense in uncertain ancestral environments. but creates problems in a world where long-term planning is essential. Understanding this doesn't eliminate the instinct, but allows us to design around it. The stakes extend to our technological future as well. As we develop increasingly sophisticated artificial intelligence, we face questions about what aspects of human cognition we want to replicate. And this requires understanding what makes human cognition unique in the first place. What if our most valuable qualities aren't just our logical reasoning capabilities, which machines can already surpass, but our intuitions, the instinctual knowledge shaped by millions of years of evolutionary trial and error, our ability to navigate complex social situations. Perhaps what we call human intuition represents an extraordinary form of pattern recognition, not a mystical sixth sense, but the product of neural adaptations refined over eons to detect subtle environmental and social cues that conscious awareness might miss. If so, the origins of these adaptations become crucial to understand, not just for historical interest, but because they represent the essence of what makes human cognition special, the foundation of qualities we might want to preserve in an increasingly automated world. There are profound philosophical implications too. If many of our behaviors, preferences, and intuitions have evolutionary origins, what does this mean for concepts like free will? Are we less autonomous than we believe, guided by ancient instincts we barely recognize? Or does understanding these instincts actually increase our freedom by allowing us to recognize and sometimes redirect these deep influences? Knowledge of our evolutionary heritage doesn't diminish our humanity. It illuminates it. The quest to understand human instincts' origins also matters because it connects us to our place in nature. We are not separate from the natural world. We are products of the same evolutionary processes that shaped all life. Our instincts are our most direct link to this heritage. In a time of environmental crisis, reconnecting with this understanding may be essential. Our instinctive attraction to certain landscapes, open views with water and shelter, likely reflects the environments where we evolved. This may explain why natural settings reduce stress and improve well-being. By understanding when and why these preferences emerged, we might better design living spaces that satisfy our innate needs, creating more sustainable relationships between human habitation and the natural world, working with our nature rather than against it. There are educational stakes as well. If many learning processes build upon instinctual foundations laid millions of years ago, our educational approaches should reflect this. Perhaps some learning difficulties represent mismatches between teaching methods and evolved cognitive patterns. For parents, understanding the evolutionary basis of childhood behaviors can be transformative. A child's fear of the dark isn't irrational. It's an adaptive response from a time when night brought real dangers. Their need for play isn't frivolous. It's how young brains have always developed essential skills. The stakes of our exploration ultimately touch on what it means to be human in the modern world, to carry instincts shaped for one environment while living in another, to be biological beings with technological extensions, to have Paleolithic emotions, medieval institutions, and godlike technology. As we journey back 5 million years tonight, we're not just reconstructing a historical timeline, we're seeking the origins of the cognitive architecture that still shapes your perceptions, decisions, and relationships today. We're looking for the first glimmers of what would become human consciousness. This quest bridges science and humanities, fact and meaning. It asks not just when our ancestors began walking upright or making tools, but when they first felt fear, curiosity, love, when they first dreamed, planned, mourned, when they first became recognizably human in their thoughts. The evidence is fragmentary, the timeline disputed. But by bringing together insights from multiple disciplines, from paleoanthropology to neuroscience, from primatology to psychology, we can begin to trace the emergence of our most fundamental human qualities. So as we continue this journey, remember what's at stake. Not just an accurate historical reconstruction, but a deeper understanding of yourself, of why you think, feel, and behave as you do, of what it truly means to be human, and of how ancient adaptations might guide our future. Chapter 3: Historical Context. To understand the dawn of human instinct, we must first set the stage. We need to visualize the world as it existed 5 million years ago, particularly in East Africa, where our evolutionary story unfolds. A world both familiar and alien to modern eyes. The late Miocene epoch was drawing to a close. Earth was cooling after a long, warm period. This global cooling was transforming environments around the planet, particularly in Africa, where forests were gradually giving way to woodlands and emerging grasslands. The African continent itself was changing. Tectonic forces were creating the Great Rift Valley, a massive geological feature that would split eastern Africa from north to south. This rifting created diverse habitats, highlands, lowlands, lakes, and valleys, within relatively small geographical areas. These environmental changes proved crucial for our story. The emerging patchwork of forests, woodlands, and grasslands created new ecological niches, new opportunities for species that could adapt, and new evolutionary pressures that would shape our ancestral line. The animal kingdom of this period would seem both familiar and strange. Many modern animal families were present, but represented by different species. Early elephants and rhinos, primitive big cats, ancestors of modern primates, all shared this transitional landscape. Among these animals were the last common ancestors of humans and chimpanzees. Creatures not yet human, not exactly chimpanzee. Their fossil record is sparse, but genetic evidence places their existence in this crucial time period. What were these creatures like? Based on comparative studies of humans and other great apes, they likely resembled chimpanzees in many ways, but with critical differences that would become more pronounced as the human lineage diverged. They were probably forest dwellers, spending time both in trees and on the ground. They likely had more ape-like proportions, longer arms, shorter legs, hands adapted for climbing. Their brains were smaller than modern humans, but larger than most other mammals. Their social structures may have resembled those of modern chimpanzees, living in communities with complex social relationships. With hierarchies, alliances, and conflicts, the foundations for the intensely social nature that would eventually define humanity. Their cognitive abilities, while not human, would have been substantial by animal standards. Problem-solving, basic tool use, social learning, and rudimentary communication were likely all within their capabilities. These formed the baseline from which human cognition would evolve. Around 7 to 5 million years ago, something momentous occurred. The lineages that would become humans and chimpanzees began to diverge. Two populations of a common ancestral species became increasingly separated, following different evolutionary paths. The exact reasons for this divergence remain debated. Geographical separation caused by changing landscapes may have played a role, as might behavioral differences that led to reproductive isolation. The fossil record offers tantalizing but incomplete evidence. What we do know is that sometime after this split, our ancestors began adapting to more open environments. This represents the first major ecological transition in human evolution, from forest-dwelling ape to woodland-adapted biped. The earliest potential members of our human lineage appear in the fossil record from this period. Sahelanthropus chadensis, about 7 million years ago. Orrorin tugenensis, about 6 million years ago. Ardipithecus, 5.8 to 4.4 million years ago. Each shows subtle anatomical changes that suggest adaptation to more upright postures. Changes in the position of the foramen magnum, where the spine connects to the skull. Pelvic architecture. Foot structures. The first steps toward bipedalism. Why bipedalism evolved remains one of paleoanthropology's great debates. Was it to see over tall grasses? To reduce sun exposure in open environments? To free hands for carrying food or tools? To improve long-distance travel efficiency? Perhaps all played a role. Whatever the specific pressures, bipedalism represents more than just a locomotor change. It represents a fundamental shift in how our ancestors interacted with their environment. A shift that would have profound implications for cognitive evolution. Standing upright changed everything. It altered the field of vision, raising the eyes to scan distant horizons rather than the forest canopy. It freed the hands for manipulation, carrying, and eventually tool use. It changed thermal regulation in open environments. But most significantly for our story, bipedalism created new cognitive demands. Balance requires sophisticated neural processing. Planning paths across open terrain differs from navigating through trees. Detecting predators in grasslands requires different attention patterns than in forests. These new cognitive challenges likely selected for changes in brain structure and function. Not immediately for larger brains, that would come later, but for neural reorganization, new connections, new ways of processing environmental information. This is where we find the first potential evidence for the dawn of uniquely human instincts. Not in dramatic brain size increase, but in subtle changes to how brains processed information about an increasingly complex and dangerous world. The transition to open environments would have dramatically changed the predator-prey dynamics for our ancestors. In forests, climbing provided escape. In open woodlands and grasslands, predators could be spotted at a distance, but escape required different strategies. This new predation pressure likely selected for heightened environmental awareness, the ability to detect subtle signs of danger, to distinguish between harmless movement and potential threats, to predict predator behavior based on limited cues. These would have been the first steps toward what we now recognize as human intuition, that inexplicable sense that something isn't right, even before conscious awareness catches up. An adaptation with clear survival value in dangerous environments. The fossil record from this period also shows the beginnings of another uniquely human adaptation, changes in dentition suggesting dietary shifts. Our ancestors were becoming more omnivorous, exploiting a wider range of food sources than their forest-dwelling relatives. This dietary flexibility would have required new cognitive abilities. Remembering locations of seasonal foods, distinguishing between safe and dangerous plant species, developing techniques to access protected food sources like nuts or underground tubers. The combination of bipedalism, expanding dietary range, and adaptation to more open environments created the perfect evolutionary pressure cooker, a situation where cognitive flexibility provided significant survival advantages, where the foundations of human instinct could emerge. By 5 million years ago, the stage was set for the accelerating cognitive evolution that would eventually produce Homo sapiens. Our ancestors weren't yet human, but they were embarking on an evolutionary path that diverged significantly from other apes. The ancestral species Australopithecus ramidus, dating to about 4.4 million years ago, offers some of our best evidence from this critical transition period. The famous RD skeleton shows a creature adapted for both tree climbing and upright walking. RD's brain was still ape-sized, about 300-350 cubic centimeters compared to modern humans' 1,300 cubic centimeters, but brain size alone doesn't tell the whole story. Neural organization and efficiency matter just as much as volume. What cognitive abilities might RD have possessed? Based on comparisons with modern primates and archaeological evidence from later periods, we can make educated inferences. They likely possessed spatial memory, rudimentary cause and effect reasoning, and social intelligence. They would have recognized group members individually, remembered social interactions, and navigated complex social relationships. These social cognitive abilities would form the foundation for the increasingly sophisticated social intelligence of later human evolution. They likely possessed basic communication abilities through vocalizations, gestures, and expressions, though not language as we understand it. They could probably coordinate group activities, warn of dangers, and express emotional states. What's most significant is that these abilities weren't just extensions of general primate cognition. They were beginning to take on uniquely hominin characteristics, shaped by the specific ecological challenges our ancestors faced in changing African environments. This brings us to a crucial question. What selective pressures might have specifically favored the development of intuitive capabilities? What aspects of this ancient environment would have rewarded individuals who could sense danger before conscious awareness? The answer likely lies in predator-prey dynamics. In open woodlands, predators could approach from multiple directions. Success or failure in detecting them often came down to seconds. Those who could process subtle environmental cues faster had significant survival advantages. Similarly, social competition within groups would have favored those who could read intentions and emotions in others, who could anticipate behaviors based on minimal cues. The foundations of what we now call emotional intelligence. As we approach the end of this historical context, we find ourselves at a fascinating juncture, the very beginning of what would become humanity. Not yet human in form or thought, but embarking on an evolutionary trajectory unlike any other species. The world 5 million years ago set the stage for this unprecedented evolutionary journey. The changing African landscape, the divergence from the chimpanzee lineage, the first adaptations to more open environments. The foundations were being laid for human instinct. In the next chapter, we'll examine the earliest evidence for these cognitive adaptations. The subtle signs in the fossil record, comparative studies and archaeological findings that suggest how and when our uniquely human instincts first began to emerge. Chapter 4. First evidence. The search for evidence of early human instinct presents unique challenges. Unlike bones that fossilize or stone tools that persist for millions of years, cognitive adaptations leave no direct physical record. We must look for indirect evidence and reasonable inferences. Our first category of evidence comes from comparative studies with our closest living relatives, chimpanzees and bonobos. By identifying cognitive abilities shared across all great apes, we can infer what capabilities existed in our last common ancestor. Chimpanzees demonstrate remarkable cognitive abilities. They use tools, recognize themselves in mirrors, remember the locations of resources, engage in complex social politics, and even show rudimentary cultural traditions that vary between groups. These shared capabilities suggest our last common ancestor already possessed substantial cognitive sophistication. The foundations upon which human instinct would build were not created from nothing. They represented extensions and modifications of existing primate cognition. But humans differ from other apes in crucial ways. We have significantly enhanced social cognition, including advanced theory of mind, the ability to understand others' mental states. We possess intuitive physics and biology, unconscious understanding of how objects and living things behave. When did these differences begin to emerge? The fossil record offers some clues, though they're subtle and require careful interpretation. Changes in brain size and structure provide our first line of evidence. Brain endocasts, molds of the interior of fossil skulls, allow paleoanthropologists to study brain shape and size in extinct species. Early hominins like Ardipithecus and Australopithecus show the beginnings of reorganization in brain structure. Specifically, we see evidence of expansion in areas associated with higher cognitive functions. Even before significant increases in overall brain size, there were changes in the proportions of different brain regions. Quality was changing before quantity. The fossil record also shows changing sensory adaptations. The position and size of eye orbits suggests shifts in visual processing, changes consistent with adaptation to more open environments where detecting distant movement would be crucial for survival. Around 3.5 million years ago, with Australopithecus species, we see the first significant increase in brain size. Still far smaller than modern humans, but beginning a trend that would accelerate in later human evolution. A trend that suggests increasing cognitive demands. What selective pressures drove these changes? Here we find our second line of evidence, the ecological context revealed through paleo-environmental reconstruction. The environments our ancestors inhabited tell us about the challenges they faced. Geological and botanical evidence shows that between 5 and 3 million years ago, Africa experienced climate fluctuations that created a mosaic landscape. Patches of forest intermixed with woodlands and emerging grasslands. Environments that required cognitive flexibility. Moving between different habitat types would have demanded different skills. Climbing in forested areas, vigilance in open spaces, memory for resource locations across a varied landscape. This environmental complexity would have favored enhanced cognitive capabilities. Predator remains found in the same deposits as early hominin fossils tell us about the dangers our ancestors faced. Large carnivores, including ancestral big cats, hyenas, and other predators, shared these landscapes, creating intense selection pressure for threat detection abilities. This brings us to perhaps the most compelling, though controversial, evidence: archaeological remains. While definitive stone tools don't appear in the record until about 2.6 million years ago, there are intriguing suggestions of earlier tool use. Microscopic wear patterns on fossilized bones from sites dating to 3.4 million years ago suggest cutting with stone tools. Though the tools themselves haven't been found from this period, the evidence implies some form of tool use earlier than previously thought. Even more tantalizing are animal bones, with marks suggesting intentional breaking to access marrow. This represents sophisticated understanding of nutritional resources and problem-solving capabilities. Early signs of the enhanced foraging intuition that would characterize later humans. What's particularly significant about early tool use isn't the technical sophistication. Early tools were simple, but what it reveals about cognitive processes. Tool creation requires mental templates, the ability to visualize an end product before it exists. It also demonstrates causal understanding, knowing how striking one stone with another produces sharp edges, and planning abilities, carrying raw materials from their source to where they're needed. These are the foundations of human intuitive thinking. A fourth line of evidence comes from stable isotope analysis of fossil teeth, which reveals information about diet. Early hominins were incorporating a wide range of foods into their diet, a flexibility that required knowing what was edible, where to find it, and how to process it. This dietary breadth suggests enhanced foraging intuition, the ability to identify new food sources and develop methods to access them, an early form of the innovative problem-solving that would become a hallmark of human cognition. When we integrate these lines of evidence, a pattern begins to emerge. Between 5 and 3 million years ago, our ancestors were developing cognitive adaptations for detecting threats in varied environments, enhanced situational awareness and danger intuition, exploiting diverse food resources, foraging intuition and problem-solving, navigating complex social groups, social intuition and early theory of mind, planning and executing multi-step processes, causal reasoning and foresight. These represent the first glimmers of distinctly human instinct, not yet at modern human levels, but beginning to diverge from the cognitive patterns of other apes, adaptations shaped by the unique ecological challenges our ancestors faced. But this evidence comes with important caveats. The fossil record from this period is still sparse. Many inferences must be made from fragmentary remains, and we must be careful not to project modern human capabilities onto ancient species. We must also consider alternative explanations. Could some of these adaptations have evolved independently in different hominin lineages? Might some apparent signs of cognitive advancement represent simpler processes? These questions continue to be debated in paleoanthropology. The most conservative interpretation would place the emergence of uniquely human instincts later in our evolutionary timeline, perhaps with Homo habilis around 2.5 million years ago, coinciding with the first definitive stone tool industries. But mounting evidence suggests the foundations were laid earlier, that the cognitive adaptations that would eventually bloom into full human consciousness began during this critical period between 5 and 3 million years ago. The dawn of human instinct. Particularly compelling is the evidence for social cognitive development during this period. Changes in canine tooth size suggest decreased male competition, possibly indicating changing social structures. The beginnings of the cooperation that would define later human societies. Sexual dimorphism, the size difference between males and females, also appears to have decreased compared to earlier ancestors, potentially indicating shifts in social organization and pair bonding, changes that would have required enhanced social cognition. These social changes may represent the most significant cognitive developments of this period. The ability to coordinate activities, share resources, and form coalitions provided survival advantages in dangerous environments. and required sophisticated social intuition. As we approach more recent time periods in the fossil record, the evidence becomes stronger. By 2.5 million years ago, with early Homo species, we see more definitive signs of enhanced cognition. Regular tool use, expanding geographic range and accelerating brain size increase. But the crucial question remains, when did the first uniquely human intuitions emerge? When did our ancestors first develop cognitive patterns that differed significantly from those of other apes? The evidence points to the period we've been exploring, 5 to 3 million years ago. This brings us to a startling possibility. What if the essence of humanity, our distinctive ways of thinking and perceiving, began not with language, sophisticated technology, or art, but with subtle shifts in how our ancestors processed information about their environment and each other? What if the cognitive foundations that would eventually enable all later human achievements were already being laid 5 million years ago in the minds of creatures that still appeared more ape-like than human? Creatures adapting to environments that demanded new ways of thinking. If true, this would fundamentally change our understanding of what makes us human. It would suggest that our most distinctive qualities aren't recent innovations, but the result of millions of years of gradual cognitive evolution, an unbroken chain of adaptations leading to modern human intuition. But just as the evidence for this early cognitive evolution seems to be solidifying, we encounter a puzzling contradiction. If these cognitive adaptations began so early, why did technological and cultural complexity develop so slowly? Why did simple stone tools remain unchanged for hundreds of thousands of years? This paradox leads us to one of the most intriguing mysteries in human evolution, a mystery that suggests something dramatic happened later in our evolutionary history, something that transformed these early cognitive foundations into the full flowering of human consciousness. What was this catalyst? When did it occur? And how did it build upon the cognitive foundations laid between 5 and 3 million years ago? These questions take us beyond our current chapter and into the heart of the human evolutionary story. As we end this first examination of evidence, we're left with tantalizing clues but no definitive answers. The fossil record reveals anatomical changes consistent with cognitive evolution. The archaeological record shows glimpses of behavioral complexity. The ecological context suggests selective pressures that would have favored enhanced intuitive capabilities. But the most compelling evidence may be found elsewhere, in your own mind, in the intuitions you rely on every day, the immediate sense of another person's emotional state, the unconscious assessment of environmental threats, the intuitive physics that lets you catch a ball. These capabilities have deep evolutionary roots, and the evidence suggests their foundations were being laid during this critical period, the dawn of human instinct, a time when our ancestors were adapting to new environments that demanded new ways of thinking. In the next section, we'll explore how these early cognitive adaptations evolved over subsequent millions of years, how they were elaborated, refined, and transformed through the emergence of different hominin species, and how they eventually culminated in the modern human mind. But the key insight from this first examination of evidence remains: what makes us distinctly human began not with technology or language, but with subtle changes in perception, attention, and information processing. Changes that laid the groundwork for all later human achievements. Chapter 5: Contradictions and Anomalies. As we deepen our exploration of early human instinct, we encounter puzzling contradictions that challenge conventional evolutionary narratives. The first of these concerns the pace of cognitive development in our ancient ancestors, a pace that seems both too slow and too fast. If basic cognitive foundations were already developing 5 million years ago, why did technological advancement proceed so glacially? Simple stone tools remained virtually unchanged for hundreds of thousands of years, a peculiar stasis difficult to reconcile with ongoing cognitive evolution. Yet simultaneously, we see evidence suggesting surprisingly advanced capabilities emerging earlier than expected. Capabilities that don't fit neatly into our linear models of gradual evolutionary progression. Anomalies that hint at a more complex developmental pattern. Consider the Lomekwi stone tools discovered in Kenya. Dating to 3.3 million years ago, these artifacts push tool use back 700,000 years earlier than previously thought, predating even the genus Homo, traditionally credited as the first true toolmakers. These tools weren't created by humans, but by Australopithecines, earlier, more ape-like ancestors. This discovery forces us to reconsider when complex planning and fine motor control first evolved, and suggests sophisticated cognitive abilities emerged earlier than once believed. But here's the contradiction. If these earlier species possessed such capabilities, why was technological progress so remarkably slow? Why do we see virtually no innovation for hundreds of thousands of years? This technological stasis presents a genuine paradox. One possible explanation involves social transmission mechanisms. Perhaps early hominins had the cognitive capacity for innovation, but lacked efficient ways to share and preserve knowledge across generations. Innovations may have been repeatedly lost rather than accumulated. This would suggest that human instinct and individual cognitive capacity evolved before our social learning systems, that our ancestors could create but not effectively teach, a limiting factor that would have dramatically slowed cultural and technological development. Another contradiction emerges when we examine brain size evolution. The traditional narrative suggests a steady increase in cranial capacity throughout human evolution. But the reality is more complex, with unexpected patterns challenging simple explanations. Some early Homo erectus specimens from 1.8 million years ago had cranial capacities reaching 1 to 100 cc, approaching the lower range of modern humans. Yet specimens from hundreds of thousands of years later sometimes show smaller brains. The progression wasn't uniformly upward. This suggests that raw brain size alone doesn't determine cognitive ability, that neural organization, connectivity, and efficiency matter as much as volume. A more nuanced understanding that allows for cognitive sophistication even in earlier, smaller-brained ancestors. Perhaps the most perplexing anomaly involves the sudden appearance of behavioral modernity. Archaeological evidence suggests that fully modern human behavior, art, symbolic thinking, complex technology, emerged relatively suddenly around 40,000 years ago. Yet anatomically modern humans had existed for at least 150,000 years prior. Why the long delay between anatomical and behavioral modernity? What triggered this relatively sudden flowering of human potential after such a prolonged period of limited cultural expression? Some researchers propose a genetic mutation affecting neural organization or language capability. Others suggest cultural rather than biological factors, that the necessary cognitive foundations were present but untapped until social or environmental conditions changed. This contradiction between gradual anatomical evolution and apparently sudden behavioral change challenges our understanding of how human cognition developed. It suggests complex relationships between biological capacity and its cultural expression. We find further anomalies when examining the geographic spread of early humans. Recent discoveries in China and elsewhere push back the dates for human dispersal from Africa, suggesting our ancestors left earlier and spread faster than previously thought. This accelerated dispersal implies greater cognitive and behavioral flexibility than expected for these time periods. The ability to adapt to dramatically different environments requires sophisticated problem-solving abilities, capabilities that seem surprisingly advanced for early Homo species. Consider the 2.1 million-year-old stone tools discovered in China. Their presence suggests hominins left Africa much earlier than once believed, successfully navigating through varied landscapes and adapting to new environmental challenges along the way. Such extensive migration would have required enhanced spatial cognition, planning abilities, and ecological understanding. Cognitive features that seem at odds with the otherwise slow pace of technological development during this period. These contradictions force us to reconsider the timeline and pattern of human cognitive evolution. The evidence increasingly suggests that many uniquely human cognitive capacities have deeper roots than previously acknowledged, roots extending back toward that pivotal 5 million year mark. Another anomaly appears in the fossil record of Homo naledi, a recently discovered species with a perplexing mix of ancient and modern features. Small-brained yet potentially practicing intentional burial, primitive in some aspects yet possibly engaging in symbolic behavior. This contradictory evidence suggests that sophisticated behaviors may have evolved independently of large brains, that some forms of complex cognition may be far older than we've recognized, undermining linear models of steady cognitive progression. The geographical distribution of early stone tools presents additional puzzles. Sites from roughly the same time period show significantly different levels of technological sophistication, suggesting considerable cognitive variation among contemporaneous hominin populations. This variation contradicts simplistic models of uniform cognitive evolution. It implies that different hominin groups developed different cognitive specializations, that human cognitive evolution wasn't a single linear progression, but a complex branching pattern. Evidence from comparative studies with great apes adds another layer of complexity. Modern research reveals capabilities in chimpanzees and bonobos that were once considered uniquely human. Tool use, rudimentary culture, and even limited symbolic thinking. These findings suggest two possibilities. Either these capabilities evolved independently in multiple lineages, or they were present in some form in our last common ancestor. Either way, they push the origins of proto-human cognition back toward that crucial 5 million year mark. Particularly intriguing are studies showing that great apes possess intuitive physics, unconscious understanding of how objects behave, and intuitive psychology, the ability to predict others' behavior based on their mental states, core components of human intuition. If these capabilities exist in modified forms across all great apes, they likely existed in our last common ancestor, suggesting that the foundations of human intuitive thinking were established before our lineages diverged and were then elaborated along different evolutionary paths. The contradiction lies in reconciling these deep cognitive roots with the apparently sudden flowering of fully modern human behavior. If the foundations were laid so early, why did their full expression take so long to emerge? The pattern that emerges from these contradictions and anomalies is one of punctuated cognitive evolution. Long periods of relative stasis interrupted by bursts of relatively rapid change. A pattern that doesn't fit neatly into either gradual or sudden evolution models. This suggests that human cognitive evolution might be better understood as a series of pre-adaptations, capabilities that evolved for one purpose but created potential for later innovations, foundations that remained latent until activated by new selective pressures. Consider bipedalism. It evolved long before tool use became common, but freed the hands for manipulation. Or social intelligence. It evolved for navigating group politics, but created neural foundations later repurposed for language and symbolic thinking. This model helps resolve the contradiction between early cognitive foundations and delayed cultural expression. The neural architecture for human cognition may have evolved gradually over millions of years, while its full cultural manifestation awaited specific triggers. These triggers might include environmental changes, population density increases, or social innovations like teaching methods. Factors that didn't change the underlying cognitive capacity but dramatically altered its expression and cultural accumulation. Our exploration of these contradictions and anomalies leads to a provocative hypothesis. That distinctly human intuition, our unique ways of perceiving, attending to, and processing information, began emerging much earlier than traditionally thought, perhaps as early as 5 million years ago. This doesn't mean our earliest ancestors possessed modern human cognition, but rather that the evolutionary foundations, the basic neural adaptations that would eventually enable fully human consciousness, were being laid during this critical transitional period. As we continue our journey, these contradictions and anomalies will serve not as roadblocks, but as signposts, pointing toward a more nuanced understanding of how human instinct emerged and challenging us to look beyond linear models of cognitive evolution. In the next chapter, we'll explore how these scientific puzzles connect to persistent myths and legends across human cultures, and examine whether these cultural narratives might preserve fragmentary memories of our species' cognitive awakening. Chapter 6. Myths and out-of-place evidence. Throughout human history, across wildly different cultures, certain mythological themes appear with striking consistency. Stories of human awakening, of consciousness bestowed or stolen, of a time when humans gained abilities that separated them from animals. These persistent narratives may hold clues, from the biblical tale of Eve eating from the tree of knowledge, to Prometheus stealing fire from the gods, to Aboriginal Dreamtime stories of ancestral beings imparting wisdom to humans. These myths share a common theme: the dramatic acquisition of uniquely human awareness. Could these widespread myths preserve cultural memories of actual cognitive transitions in human evolution? Might they reflect our ancestors' awareness that something profound had changed in how humans perceived and interacted with their world? Anthropologists have long recognized that myths often encode practical knowledge and historical events, information vital for survival, passed down through memorable narratives. Could they also preserve memories of our species' cognitive development? This isn't to suggest literal interpretations of ancient myths, but rather to consider whether these stories might metaphorically reflect real evolutionary transitions. Cultural memories of moments when human consciousness expanded in noticeable ways. Consider the Prometheus myth, where fire represents not just literal flame but the dawning of technology and higher awareness. This parallels archaeological evidence of controlled fire use appearing around 1.5 million years ago. A development that transformed human evolution. Fire provided warmth, protection from predators, and the ability to cook food. Cooking increased caloric availability, potentially fueling brain growth. It may have represented a key cognitive threshold that lived on in cultural memory as stories of stolen knowledge. Similarly, the widespread myths of communication with animals in a primordial time might reflect memories of a period when human cognitive separation from other species was less pronounced, when intuitive understanding of animal behavior was more essential for survival. These cultural narratives gain particular significance when we consider out-of-place archaeological evidence, findings that don't fit neatly into conventional timelines of human cognitive development. Artifacts suggesting capabilities that shouldn't exist at certain time periods. Among the most intriguing are the geometric patterns found at multiple archaeological sites dating to periods before Homo sapiens. Engravings on bones and stones showing intentional, non-random patterns, suggesting symbolic thinking in pre-human species. The Bildungsleben engravings from Germany, associated with Homo heidelbergensis and dating to approximately 400,000 years ago, show systematic linear patterns, too regular to be accidental tool marks, suggesting intentional creation of abstract designs. Similarly, the zigzag engravings found on a shell from Trinil, Java, date to around 500,000 years ago and are attributed to Homo erectus. These markings appear to be intentionally created geometric patterns, evidence of abstract thinking in a non-human species. These findings contradict the traditional view that symbolic thinking emerged relatively recently with Homo sapiens. They suggest earlier species possessed cognitive capabilities once thought unique to modern humans, capabilities that might include abstract thought and symbolism. Even more provocative are potential signs of ritual behavior in non-human species. The careful arrangement of cave bear skulls by Neanderthals. The Homo naledi remains deposited deep within nearly inaccessible cave chambers, suggesting intentional body disposal. These behaviors hint at some form of symbolic thinking, awareness of death, and perhaps spiritual concepts in non-human species. Cognitive capacities traditionally associated only with Homo sapiens, forcing us to reconsider when these capabilities first emerged. What makes these findings particularly relevant to our exploration is their connection to intuitive cognition. Symbolic thinking and ritual behavior represent externalized expressions of internal intuitive processes, ways of making sense of the world beyond mere survival needs. When we connect these archaeological anomalies with persistent mythological themes, a pattern begins to emerge. Both suggest that cognitive transitions occurred at multiple points in hominin evolution, and that some of these transitions may have been noticeable enough to be preserved in cultural memory. This brings us to one of the most persistent cross-cultural myths: stories of interbreeding between humans and non-human beings, found in Greek, Mesopotamian, Hindu, Native American, and numerous other mythological traditions, often describing unions between humans and godlike or animal-like entities. Remarkably, modern genetic evidence confirms interbreeding between different hominin species. Homo sapiens interbred with Neanderthals, Denisovans, and possibly other archaic human species. Scientific confirmation of something mythology had long suggested. Could these widespread myths preserve cultural memories of actual contact between different hominin species? Encounters between populations with different cognitive capabilities and physical appearances? Meetings that would have seemed extraordinary enough to become embedded in oral tradition. These interbreeding events may represent crucial moments in human cognitive evolution. Genetic evidence suggests that some archaic human genes related to brain development were selectively retained in modern human populations, possibly conferring cognitive advantages. This genetic evidence offers a potential mechanism for punctuated cognitive evolution. Hybridization between hominin species with different cognitive adaptations could have produced new combinations of neural traits, potentially accelerating cognitive development in hybrid offspring. Another category of out-of-place evidence involves technological capabilities appearing earlier than expected, like the sophisticated Acheulean hand axes that first appeared around 1.76 million years ago. Tools requiring considerable planning and fine motor control to create. The complexity and standardization of these tools suggest cognitive capabilities seemingly at odds with the otherwise slow pace of technological change during this period. Advanced planning, mental templates, and aesthetic sensibility beyond what we might expect. What's particularly striking is that once this technology emerged, it remained virtually unchanged for over 1 million years. A stasis difficult to explain if the toolmakers possessed the cognitive flexibility and innovation we associate with fully modern humans. This paradoxical combination, sophisticated capabilities alongside extremely slow innovation, suggests a form of intuitive intelligence different from our own, perhaps specialized rather than generalized, deep rather than broad. A different kind of consciousness. We find similar paradoxes in the recent discoveries regarding Neanderthal capabilities. Cave art, complex adhesives, medicinal plant use, and symbolic behaviors suggest cognitive sophistication. Yet their technology remained relatively static compared to contemporaneous Homo sapiens. These findings challenge our species-centric view of intelligence. They suggest that different hominin species evolved different forms of cognition, each with their own strengths and limitations, each representing a different evolutionary experiment in consciousness. This brings us back to mythology and its possible connection to evolutionary memory. Many cultural traditions include stories of multiple human or semi-human races, beings with different capabilities and appearances, often described as existing in an ancestral time. From Norse myths of elves and dwarves, to Aboriginal stories of different types of ancestral beings, to Greek tales of cyclopes and other semi-human races, these myths might preserve cultural memories of times when multiple hominin species coexisted. The persistence of these myths across cultures, separated by vast distances and time, suggests they might contain kernels of truth. Not literal truth, but cultural memories of significant evolutionary events. Memories of a time when human consciousness was still in formation. What's particularly relevant to our exploration of human instinct is how these myths often focus on differences in knowledge and perception rather than just physical appearance. They frequently describe beings with special abilities to communicate with animals, read natural signs, or see hidden aspects of reality. These descriptions parallel what we might expect if different hominin species possessed different specialized forms of intuitive cognition. If Neanderthals, for instance, had enhanced spatial awareness or different sensory sensitivities compared to Homo sapiens. The myths and out-of-place evidence together suggest a more complex picture of human cognitive evolution than traditionally acknowledged. Not a single linear progression, but multiple paths, interactions, and transitions. A mosaic of cognitive adaptations developing at different rates in different populations. This complexity helps explain the contradictions we encountered in the previous chapter. The apparently rapid dispersal alongside slow technological change, the evidence for symbolic thinking in pre-human species. The puzzling combination of sophisticated abilities and limited innovation. As we integrate these diverse lines of evidence, archaeological anomalies, genetic findings, and cross-cultural mythological themes, we begin to see the outlines of a new narrative of human cognitive evolution. One that places the dawn of human instinct much earlier and develops much more complexly than traditionally thought. This narrative suggests that distinctly, human intuition didn't emerge in a single evolutionary moment, but through a series of transitions, some gradual and some relatively rapid, each building upon previous adaptations, each preserved perhaps in cultural memory as myths of awakening. In the next chapter, we'll explore what these findings mean for our understanding of ourselves, how recognizing the ancient roots of human instinct transforms our perspective on what makes us human, and what it means for our future as a species. Chapter 7, Stakes Escalation. As we've pieced together evidence from fossils, artifacts, genetics, and cultural narratives, the stakes of our exploration have dramatically increased. What began as an investigation into the origins of human instinct has evolved into something far more profound, a fundamental reassessment of human nature itself. If the foundations of human intuition were laid much earlier than traditionally thought, perhaps as early as 5 million years ago, and developed through a complex, non-linear process, then our understanding of ourselves requires radical revision, with implications extending far beyond academic interest. The evidence suggests we are not the recent cognitive revolutionaries we've believed ourselves to be, but inheritors of ancient neural adaptations that have been refined, recombined, and repurposed over millions of years. A realization that transforms how we understand our place in nature. This revised understanding raises existential questions about what it means to be human. If many of our supposedly unique cognitive traits have deep evolutionary roots shared with extinct hominin species, if our consciousness represents just one possible configuration of cognitive adaptations, then what truly sets us apart? The stakes escalate further when we consider the implications for artificial intelligence development. Current AI approaches attempt to replicate human reasoning through computational power and algorithmic processing, but largely ignore the intuitive foundations that may be central to human cognition. If human intelligence emerged not primarily through logical reasoning capabilities, but through intuitive processing shaped by millions of years of environmental interaction, then our approaches to AI might be fundamentally misguided, missing the essence of what makes human cognition unique and powerful. This realization comes at a critical juncture in technological development. As AI systems grow increasingly sophisticated, understanding the true nature of human cognition becomes essential. Not just for creating more effective technologies, but for ensuring they complement rather than undermine human capabilities. The stakes extend to education as well. Our current educational systems heavily emphasize abstract reasoning and fact accumulation, but potentially undervalue the intuitive knowledge acquisition systems that may have been central to human cognitive evolution. If human learning evolved primarily through observation, imitation, and experiential knowledge rather than explicit instruction, if our brains are optimized for intuitive pattern recognition rather than sequential logical processing, then many educational difficulties may stem from mismatches between teaching methods and evolved learning mechanisms. This could explain why some children struggle in traditional classroom settings, yet display remarkable learning capabilities in real-world contexts. Why information presented abstractly often fails to transfer to practical application. Why embodied, experiential learning frequently proves more effective and engaging. Understanding the true evolution of human cognition might transform educational approaches, leading to methods that work with rather than against our evolved learning tendencies, potentially alleviating learning difficulties and enhancing educational outcomes across diverse populations. The health implications are equally profound. Many contemporary mental health challenges may represent mismatches between our evolved cognitive adaptations and modern environments. Depression, anxiety, attention deficits, these might be partly responses to conditions radically different from those we evolved to navigate. If human instinct was shaped for small social groups, natural environments, and direct feedback loops, then today's large anonymous societies, artificial settings, and complex delayed consequences may place enormous stress on our cognitive architecture, creating the epidemic of mental health challenges we currently face. This perspective suggests new approaches to psychological well-being, not just treating symptoms, but redesigning environments to better match our evolved cognitive needs, creating settings that support, rather than strain, our intuitive processing systems. The stakes escalate further when we consider implications for social organization. If human intuition evolved primarily for small group interactions, if our instinctual responses to threat, resource distribution, and social hierarchies were calibrated for band-level societies, then many contemporary social tensions may reflect predictable mismatches. This could explain why modern political systems struggle with large-scale cooperation, why tribal thinking persists despite globalization, why wealth inequality triggers such powerful emotional responses. Our instincts may be operating according to parameters set millions of years ago. Understanding these instinctual foundations could transform approaches to governance, economic systems, and conflict resolution, not by overriding our evolved tendencies, but by designing systems that work with them, creating social structures aligned with, rather than opposed to, our cognitive architecture. The environmental implications may be most urgent of all. Our difficulty responding effectively to climate change and ecological degradation might stem from mismatches between evolved risk assessment systems and modern environmental threats. Our instincts were calibrated for immediate visible dangers, not gradual statistical risks. If human intuition evolved to respond to immediate threats like predators, rather than long-term invisible dangers like carbon emissions, then our environmental crisis may partly reflect limitations in our evolved cognitive architecture. Limitations we must understand to overcome. This perspective offers new approaches to environmental action, not just presenting facts and figures, but framing issues in ways that engage evolved risk-response systems, making abstract threats concrete and immediate, working with rather than against our intuitive psychology. As the stakes of our exploration escalate, we must also consider philosophical implications. If human consciousness emerged gradually through evolutionary processes, if our seemingly unique cognitive capabilities have deep prehistoric roots, then sharp distinctions between human and animal minds become increasingly untenable. This challenges anthropocentric worldviews that place humans entirely apart from nature. It suggests a cognitive continuum rather than a binary division, with profound implications for ethics, rights, and our relationship with other species. Yet even as this revised understanding appears to diminish human uniqueness, it simultaneously reveals something remarkable. The extraordinary evolutionary journey that produced our particular form of consciousness, a journey spanning millions of years and countless environmental challenges. This journey wasn't the straight line of progressive improvement often portrayed in popular accounts, but a complex branching path with multiple experimental lineages, dead ends, and remarkable innovations. Gradual adaptations punctuated by moments of relatively rapid change. What emerges is a new appreciation for the wonder of human consciousness, not as a recent miracle that separated us from nature, but as the product of ancient processes working through natural selection to create something extraordinary, something whose origins stretch back to that crucial period 5 million years ago. The stakes reach their highest point when we consider implications for humanity's future. If we truly understand the evolutionary foundations of our cognitive architecture, if we recognize both its power and its limitations, then we gain unprecedented ability to shape our continued development. For the first time in evolutionary history, a species can comprehend its own cognitive design, can recognize the adaptations that shaped it, can identify mismatches between evolved tendencies and current challenges, and can consciously direct its future cognitive development. This represents an evolutionary transition unlike any before, from unconscious adaptation through natural selection to conscious self-direction. A transformation that makes understanding our cognitive origins not just academically interesting, but existentially essential. The choices we make in coming decades about technology, education, social organization, and environmental action will shape human cognitive evolution far more rapidly than natural selection. But making wise choices requires understanding what we're working with, the cognitive architecture built over millions of years of evolution. This is why tracing human instinct to its origins 5 million years ago matters so profoundly. Not just to satisfy historical curiosity, but to guide our species' future, to ensure we build upon rather than undermine the cognitive foundations that made us human in the first place. As we stand at this evolutionary crossroads, evidence is emerging that challenges our most basic assumptions about human uniqueness. Findings that suggest our cognitive separation from other species may be less absolute than we've believed. That other forms of consciousness existed and potentially still exist alongside our own. Recent research with great apes reveals capabilities once thought uniquely human. Ravens show signs of recursive thinking once considered exclusive to human language. Dolphins demonstrate self-awareness and cultural transmission. Elephant communities mourn their dead and help their injured. These discoveries suggest we exist on a cognitive continuum rather than standing apart from all other minds. That consciousness comes in many forms, each adapted to different evolutionary pressures. And that human intuition represents just one possible configuration of cognitive adaptations. This perspective fundamentally changes the stakes of our exploration. We're no longer just investigating the origins of human instinct, but seeking to understand consciousness itself in its many manifestations, with implications for how we relate to all minds, biological and potentially artificial. But perhaps the most startling evidence, the finding that escalates the stakes beyond all previous considerations, comes from recent genetic and archaeological discoveries. Findings that suggest the story of human cognitive evolution is far more complex than we've recognized. The sequencing of Neanderthal and Denisovan genomes revealed interbreeding between these archaic humans and Homo sapiens, with some of the retained genes relating to brain development and function, suggesting the possibility that cognitive adaptations were shared between species. More provocatively, there's growing evidence that different hominin species coexisted for hundreds of thousands of years, that Homo sapiens lived alongside Neanderthals, Denisovans, Homo floresiensis, and potentially other archaic human species until relatively recently. This extended coexistence raises a profound possibility that for most of human evolution, multiple forms of consciousness existed simultaneously. Different cognitive architectures adapted to different ecological niches, various experiments in what it meant to be human. The implications are staggering. Human consciousness as we know it may be just one survivor of many cognitive experiments, one form among several that once existed, and potentially not the only form that could exist in the future. This realization fundamentally transforms the stakes of our investigation. We're no longer just exploring the origins of our own cognition, but uncovering a lost world of different minds, different ways of experiencing and understanding reality that once existed alongside our own. What might we learn from these lost cognitive architectures? What capabilities might they have possessed that we lack? What alternative paths of consciousness development might they represent? And what does their disappearance tell us about the fragility of consciousness itself? As we stand on the precipice of creating artificial intelligences and potentially modifying our own biology, these questions take on urgent significance. Understanding the full spectrum of possible conscious experiences becomes essential for making wise choices about humanity's cognitive future. And this brings us to the most provocative evidence of all, findings that suggest the story of human consciousness might be even more extraordinary than we've imagined. Evidence that points toward moments of relatively sudden cognitive transition. evolutionary inflection points that transformed how our ancestors perceived and interacted with reality. Recent genetic studies have identified gene variants related to neural development that show signs of strong positive selection during key periods of human evolution, mutations that spread rapidly through populations, suggesting they conferred significant advantages. These genetic shifts coincide with archaeological evidence of behavioral changes, new technological innovations, expanded geographical range, increased cultural complexity, suggesting moments when cognitive capabilities might have transformed relatively quickly. What if human consciousness as we know it emerged not through gradual accumulation of small changes, but through a series of relatively rapid transitions? Moments when new cognitive capabilities emerged and transformed how our ancestors experienced the world. This possibility brings us full circle to those persistent cross-cultural myths, stories of awakening, of knowledge gained, of transitions from one state of awareness to another. Perhaps these narratives preserve cultural memories of actual cognitive transitions experienced by our ancestors. As we prepare to examine this evidence more closely in our next section, we stand at a profound juncture in our understanding of human nature. The stakes have escalated from historical curiosity to existential significance, from academic interest to the future of consciousness itself. Chapter 8. Competing Theories. As we approach the climax of our exploration into the dawn of human instinct, we must confront the competing theories that attempt to explain when and how our uniquely human cognitive architecture first emerged. Each theory supported by evidence, each with significant implications for our understanding of what makes us human. The first major theory, what we might call the recent revolution hypothesis, places the emergence of distinctly human cognition relatively late in our evolutionary timeline. According to this view, anatomically modern humans existed long before behaviorally modern humans appeared. Proponents point to the apparent explosion of symbolic behavior, complex technology, and artistic expression that appears in the archaeological record around 40,000 years ago. This cultural Big Bang coincides with Homo sapiens' successful expansion across the globe. They argue that a relatively sudden neural reorganization, perhaps through a fortunate genetic mutation affecting language or abstract thinking, transformed our species from anatomically modern but cognitively limited beings into the symbolically minded humans we are today. This theory draws support from the apparent discontinuity in the archaeological record. The relatively sudden appearance of cave art, figurines, musical instruments, and dramatically diversified tool technologies, a flowering of symbolic expression seemingly without clear precedents. It also aligns with genetic evidence suggesting positive selection on certain genes related to neural development during this period, particularly genes involved in language processing and social cognition, suggesting biological changes may have enabled this cultural revolution. The strength of this theory lies in its explanatory power for the archaeological evidence. If distinctly human cognition emerged relatively recently and suddenly, it would explain the apparent explosion of cultural complexity and the subsequent acceleration of technological innovation. However, this theory struggles to explain evidence of sophisticated behaviors predating this revolution. The recently discovered cave art from Indonesia, dating to at least 44,000 years ago, complex Neanderthal technologies, and early evidence of symbolic thinking in other hominin species. This brings us to the competing deep roots hypothesis. This theory argues that distinctly human cognitive capacities emerged gradually over millions of years, with foundations dating back to that crucial period around 5 million years ago when our lineage diverged from other apes. According to this view, what we call human intuition represents the accumulated adaptations of countless generations facing diverse environmental challenges, not a recent revolution, but a long evolutionary process of neural refinement and specialization. Proponents point to evidence of cognitive sophistication in early hominin species. The planning required for Acheulean hand axe production 1.7 million years ago, the control of fire dating back hundreds of thousands of years, the complex foraging strategies evident in diverse hominin adaptations. They argue that many supposedly unique human cognitive abilities exist in rudimentary forms in other great apes. Tool use, cultural transmission, rudimentary theory of mind, and even symbolic communication, suggesting these capabilities were present in ancestral forms in our last common ancestor. This theory aligns well with evolutionary principles. Complex adaptations rarely emerge suddenly, but develop through modification of existing structures. Human cognitive capabilities would have evolved through incremental adaptations to changing environmental pressures. It also explains the cognitive capabilities of extinct hominin species. If distinctly human cognitive processes began emerging millions of years ago, then Neanderthals and other archaic humans would naturally share many of these capabilities. As recent archaeological evidence suggests they did, the strength of this theory lies in its evolutionary plausibility and explanatory power for the full range of archaeological evidence. It explains both the apparent cognitive sophistication of early hominins and the long periods of technological stasis. However, it struggles to explain the apparent acceleration of cultural innovation in recent human history. If the cognitive foundations were in place for millions of years, why did technological and cultural complexity increase so dramatically only in the past 50,000 years? This brings us to a third theory that attempts to reconcile these competing views, what we might call the potential and expression hypothesis. This theory suggests a distinction between cognitive potential and its cultural expression, between capability and manifestation. According to this view, the neural foundations for human cognition evolved gradually over millions of years, but their full expression required specific environmental, social, and demographic conditions that emerged only recently in our evolutionary history. Proponents point to evidence that small isolated populations rarely develop complex cultural innovations regardless of cognitive potential. That technological advancement accelerates with population density and interconnection, as ideas combine and build upon each other. They note that the Cultural Revolution, around 40,000 years ago, coincided with increasing population densities and social networks in Europe, creating conditions where existing cognitive capabilities could find fuller expression through cultural accumulation and transmission. This theory draws support from mathematical models of cultural evolution, which demonstrate that innovation rates depend not just on individual creativity, but on population size, interconnectedness, and effective transmission mechanisms, factors that changed dramatically during recent human history. It also aligns with evidence of sophisticated behaviors in isolated instances long before they became widespread, like the 100,000-year-old shell beads and ochre processing at Blombos Cave, suggesting the cognitive capabilities existed before their consistent cultural expression. The strength of this theory lies in its ability to reconcile seemingly contradictory evidence. It explains both the deep evolutionary roots of human cognitive potential and the relatively recent flowering of cultural complexity, without requiring sudden neural reorganization. But it raises profound questions about the relationship between biological and cultural evolution, about whether modern human cognition can be understood apart from its cultural expression, about the extent to which our minds have been shaped by our own cultural creations. As we weigh these competing theories, we must consider not just which best fits the evidence, but which offers the most complete explanation for the full range of human cognitive capabilities. From our intuitive understanding of physical objects to our capacity for symbolic thought, the question becomes not just when distinctly human cognition emerged, but what cognitive adaptations truly define humanity, and whether these emerged as a package or developed at different rates in response to different selective pressures. Recent evidence increasingly points toward a synthesis of these perspectives, suggesting that human cognitive evolution combined gradual adaptation with periods of relatively rapid change. That different cognitive capabilities emerged at different times in response to different pressures. What we call human instinct may represent not a single adaptation, but a constellation of specialized intuitive systems, each with its own evolutionary history, each emerging in response to specific environmental challenges faced by our ancestors. Intuitive physics, our unconscious understanding of how objects behave, likely has extremely deep roots, shared to some degree with all primates and even other mammals, a necessary adaptation for moving through complex environments. Intuitive biology, our capacity to reason about living things differently than non-living objects, also appears widespread across species, though humans show particularly sophisticated categorization systems, adaptations perhaps related to our omnivorous foraging strategies. Social intuition, our ability to read intentions and emotions, to predict behavior based on mental states, shows more specifically hominin elaboration. Though foundational aspects exist in other primates, its development likely accelerated with increasing social complexity. Intuitive communication, our capacity to infer meaning from gestures, expressions, and vocalizations, also builds on primate foundations but reached unprecedented sophistication in humans, possibly through co-evolutionary processes between brain development and cultural innovation. As we integrate these insights, a new picture emerges. Human intuition as a mosaic of cognitive adaptations, some ancient, some recent, some shared with other species, some uniquely elaborated in the human lineage, all working together to create our distinctive way of understanding the world. This mosaic theory, drawing elements from all three competing hypotheses, offers our most complete explanation for the origins of human instinct and provides a framework for understanding both our cognitive connection to other species and our unique mental capabilities. Chapter 9. New Science and Paradoxes. Recent scientific advances are transforming our understanding of human cognitive evolution. New archaeological discoveries, improved dating methods, ancient DNA analysis, and comparative cognitive studies all converge to suggest a more complex picture than previously recognized. One that challenges traditional narratives but reveals a more fascinating story. Perhaps most revolutionary are the insights from ancient DNA studies. The sequencing of Neanderthal and Denisovan genomes revealed not just that these archaic humans interbred with Homo sapiens, but that specific gene variants related to brain function were selectively retained. This suggests a profound possibility that modern human cognition represents a hybrid architecture, drawing elements from multiple hominin lineages, each adapted to different environments and potentially offering different cognitive specializations. Particularly intriguing are FOXP2 gene variants involved in speech and language processing. Neanderthals shared with Homo sapiens two critical mutations absent in chimpanzees, suggesting language capabilities may have emerged in the common ancestor of humans and Neanderthals. Yet Neanderthals lacked certain other modern human variants in genes regulating brain development. The modern variants showing signs of positive selection within the past 50,000 years, potentially explaining aspects of our distinct cognitive phenotype. These genetic insights create the first paradox of human cognitive evolution. Our minds appear to be simultaneously ancient and recent, built on foundations millions of years old, yet transformed by relatively recent adaptations, both deeply rooted and newly emerged. New archaeological discoveries further complicate the picture. Intentional use of pigments by Neanderthals dating to 250,000 years ago. Shell engravings by Homo erectus from 500,000 years ago. Sophisticated wooden tools preserved at Schoningen from 300,000 years ago. These findings suggest that behaviors once considered markers of modern human cognition actually preceded Homo sapiens. That symbolic thinking, planning depth, and technical sophistication have deeper roots than previously acknowledged, creating another paradox in our understanding. Equally transformative are recent advances in comparative cognitive science, studies revealing unexpected capabilities in great apes and other animals, chimpanzees manufacturing and using tools in multi-step sequences, crows solving causal reasoning problems, dolphins recognizing themselves in mirrors. These capabilities suggest that what we consider uniquely human cognition might better be understood as elaborations of existing primate adaptations, differences of degree rather than kind. creating a third paradox, our continuity with and distinction from other minds. Perhaps most significant are new insights into human cognitive development. Studies showing that human infants possess intuitive understanding of physics, biology, and psychology from the earliest ages. Knowledge that appears too early to be learned through experience alone. This suggests that key aspects of human intuition are innate, built into our cognitive architecture, not created through cultural learning, but emerging through interaction between genetic predispositions and environmental triggers. A fourth paradox, knowledge that precedes experience. Cognitive neuroscience provides additional insights through studies of intuitive decision-making. Research showing that our brains often reach correct conclusions before conscious reasoning. That expert intuition represents pattern recognition occurring below conscious awareness. These findings suggest that much of human cognition operates through rapid, unconscious processing. That what we experience as intuition or instinct may represent sophisticated neural computation operating beyond conscious access. A fifth paradox, unconscious wisdom. Together, these scientific advances create a new understanding of human intuition, not as a mystical capacity, but as the product of specialized neural systems shaped by millions of years of evolutionary pressures. Systems that operate largely below conscious awareness. This new understanding forces us to reconsider when distinctly human cognition first emerged. If many of our cognitive capacities operate through unconscious intuitive systems with deep evolutionary roots, then the dawn of human instinct likely extends much further back than traditionally thought. The evidence increasingly points toward that crucial period around 5 million years ago, when climate changes were transforming East African environments from forests to mixed woodlands and emerging grasslands, creating novel selective pressures on our earliest ancestors. During this period, we see the first anatomical adaptations toward bipedalism, changes that would free the hands for manipulation and tool use, that would alter the field of vision and predator-prey dynamics. That would change everything about how our ancestors interacted with their environment. These environmental and anatomical changes would have created new cognitive demands, new ways of perceiving, attending, remembering, and predicting. The first subtle shifts in neural processing that would eventually blossom into human consciousness. But here we encounter another paradox. If the foundations of human cognition began emerging so early, why did technological and cultural innovation proceed so slowly for millions of years? Why the long delay between cognitive potential and cultural expression? Recent studies of cultural evolution provide a potential answer. Mathematical models demonstrating that innovation rates depend not just on individual cognition, but on population density, interconnection, and transmission fidelity. Factors that remained limited for most of human evolution. This creates a distinction between cognitive capability and its cultural manifestation, between what individual minds could conceive and what collective culture could sustain, explaining both the early emergence of human cognitive potential and its delayed expression in material culture. This distinction helps resolve the paradox of Neanderthal cognition. Evidence suggests they possessed sophisticated capabilities, complex adhesives, medicinal plant knowledge, possible symbolic practices. Yet their technology remained relatively stable compared to contemporary Homo sapiens. The difference may lie not in individual cognitive potential, but in demographic and social factors affecting cultural accumulation. Neanderthal populations were smaller, more isolated, and possibly had different information transmission practices, limiting their cultural expression despite sophisticated cognition. This brings us to perhaps the most profound paradox of human cognitive evolution, the relationship between biological and cultural inheritance, between genes and ideas, between the slow pace of genetic evolution and the accelerating pace of cultural change. For most of hominin evolution, biological and cultural inheritance proceeded at comparable rates. But in recent human history, cultural evolution has dramatically outpaced genetic change, creating an unprecedented situation where minds shaped for one environment must navigate radically different conditions. This acceleration creates what we might call the paradox of modern human cognition. We possess Stone Age minds, navigating Space Age challenges. Intuitive systems calibrated for immediate, concrete threats, facing novel, abstract problems, creating both our greatest achievements and our most perplexing failures. Our intuitive physics helps us catch balls, but struggles with quantum mechanics. Our intuitive biology recognizes animals, but resists evolutionary thinking. Our social intuition navigates small group politics, but falters with global cooperation. Our intuitive probability assessment manages everyday risks, but misinterprets statistics. These mismatches between evolved intuition and modern challenges define the human condition in technological societies, creating cognitive blind spots where our instincts lead us astray, yet simultaneously enabling the cultural innovations that distinguish our species. What's emerging from these scientific advances is a new understanding of human cognition as a hybrid system, combining ancient intuitive processes with more recent capacities for abstract, symbolic thought, each operating according to different principles, each with different evolutionary histories. Our intuitive systems appear to have deep roots, emerging gradually over millions of years of hominin evolution, while our capacity for abstract reasoning and symbolic representation may have accelerated more recently through gene-culture coevolution, creating our distinctive cognitive architecture. This hybrid nature creates another paradox. We are simultaneously intuitive and analytical beings. Our understanding of the world combines immediate, unconscious insight with deliberate, conscious reasoning, often creating internal conflicts when these systems reach different conclusions. Modern neuroscience supports this dual process view, identifying distinct neural systems for intuitive versus analytical thinking. Systems that sometimes cooperate and sometimes compete, that respond differently to environmental triggers and cultural training. This dual architecture may explain the paradoxical nature of human consciousness itself, our simultaneous experience of being embedded within nature, yet somehow separate from it, of being biological creatures with transcendent aspirations, of being both determined by our evolutionary past and free to imagine alternative futures. As we integrate these scientific advances, a new picture emerges of when and how human instinct first dawned, not in a single evolutionary moment, but through a series of adaptations spanning millions of years. Beginning with that crucial transition around 5 million years ago, the earliest foundations were likely adaptations for threat detection in more open environments, enhanced attention to movement, more sophisticated spatial mapping, improved predator avoidance strategies, cognitive changes leaving no direct trace in the fossil record. These were followed by adaptations for social coordination, more complex communication systems, enhanced theory of mind, sophisticated coalition tracking, adaptations visible indirectly through changing patterns of group size and resource exploitation. Later came adaptations for technological innovation, mental templates for tool creation, causal understanding, teaching capacities, changes we can track through the archaeological record of increasingly sophisticated material culture. Finally, relatively recently in our evolutionary history, came the capacity for symbolic thought and abstract reasoning, abilities that may have emerged through gene-culture coevolution as human populations grew larger and more interconnected, creating the conditions for language and cultural acceleration. This sequence, from enhanced environmental awareness to social coordination to technological innovation to symbolic thought, represents not distinct stages, but overlapping adaptations, each building upon and modifying what came before, creating the mosaic of human intuition. The paradox that emerges from this new understanding is that human intuition is both our oldest and newest cognitive adaptation, ancient in its foundations, yet continuously modified through ongoing interaction between biological and cultural evolution, a living system still in development. Chapter 10. The Big Reveal. Throughout this exploration, we've been circling a profound revelation about human instinct, drawing together evidence from paleontology, archaeology, genetics, neuroscience, and anthropology. building toward an understanding that fundamentally transforms how we see ourselves. The big reveal has been hiding in plain sight. Human instinct did not emerge in a single evolutionary moment. It was not the product of a cognitive revolution that suddenly separated us from other species. It represents something far more extraordinary, the accumulation of countless adaptations across millions of years, each responding to specific environmental challenges. What makes this understanding revolutionary is not just its time frame, but its implications. If human intuition began emerging around 5 million years ago and developed through a complex, non-linear process, then our consciousness is far more deeply connected to the natural world than we've recognized. The traditional narrative of human exceptionalism, that we stand apart from nature due to our unique cognitive capacities, dissolves when we recognize the evolutionary continuity of our mental processes. Our instincts were shaped by the same forces that shaped all life, through the same mechanisms. This doesn't diminish human uniqueness, but places it in proper context. We aren't separate from nature, but represent one fascinating expression of what consciousness can become when shaped by specific evolutionary pressures. Our particular form of awareness is just one possibility among many. The big reveal is this: what we experience as distinctly human intuition, our unconscious understanding of objects, organisms, minds, and relationships, represents the accumulated wisdom of countless generations interacting with their environments. A form of evolutionary knowledge embedded in our neural architecture. When you intuitively understand that a falling object will follow a parabolic trajectory, when you unconsciously recognize a living organism versus an inanimate object, when you effortlessly read someone's emotional state from subtle facial cues, you're accessing knowledge acquired over millions of years. These intuitive capacities didn't require explicit instruction. You didn't need physics lessons to catch a ball or psychology training to recognize anger. These understandings emerged naturally through the interaction between your evolved neural architecture and environmental experience. This represents a profound form of inherited knowledge, not consciously articulated, but embedded in the structure of your cognitive systems. Knowledge acquired not through individual learning, but through the collective experience of our evolutionary lineage. Wisdom accumulated across geological time. The revelation transforms how we understand knowledge itself. Beyond what we consciously learn exists this deeper reservoir of evolutionary wisdom. Information about how the world works, encoded not in books or equations, but in the very structure of our perceptual and cognitive systems. This evolutionary knowledge operates differently than conscious learning. It processes information holistically, rather than sequentially. It recognizes patterns without breaking them into components. It reaches conclusions without conscious deliberation. It knows without knowing how it knows. This is why intuition often outperforms conscious reasoning in complex situations. Why expert intuition can reach correct conclusions faster than analytical thinking. Why we sometimes sense danger before consciously identifying threats. Our intuitive systems access pattern recognition capabilities refined over evolutionary time. The big reveal extends further. This evolutionary knowledge wasn't designed solely for truth-seeking. It was shaped for survival and reproduction in specific ancestral environments, creating both remarkable insights and systematic biases, both powers and limitations. Our intuitive physics works brilliantly for medium-sized objects at moderate speeds, the conditions our ancestors encountered, but breaks down at quantum or cosmic scales. Our intuitive biology recognizes animals efficiently, but resists understanding evolution. Our social intuition navigates interpersonal dynamics, but struggles with global cooperation. These limitations aren't flaws, but design constraints. Our intuitive systems evolved for specific contexts, not universal truth-seeking. They represent optimizations for ancestral environments, not general-purpose reasoning systems, creating both our greatest strengths and most persistent cognitive blind spots. This understanding resolves the paradox of human irrationality. Why sophisticated minds capable of landing spacecraft on distant planets still fall prey to superstition, tribalism, and cognitive biases. Why scientific thinking feels unnatural while magical thinking comes easily. We're running ancient software on modern problems. The big reveal transforms our understanding of consciousness itself. What we experience as awareness emerges from the integration of these intuitive systems that operate largely beyond conscious access, that process information according to principles shaped by evolutionary history rather than logical rules. This doesn't reduce consciousness to mere computation. Rather, it reveals consciousness as something far more extraordinary, the product of billions of years of evolutionary refinement, a process that connected organisms to their environments in increasingly sophisticated ways, culminating in our particular form of self-awareness. The revelation carries profound implications for artificial intelligence. If human intelligence emerges from intuitive systems shaped by embodied interaction with environments over evolutionary time, then replicating human-like intelligence may require more than computational power and algorithms. It suggests that truly human-like AI might require embodied experience in physical environments, the development of intuitive systems through interaction with the world, processes that can't be shortcut through pure computation, a humbling recognition of the complexity underlying natural intelligence. This understanding also transforms our approach to education. If much human knowledge operates through intuitive systems rather than explicit reasoning, then education should engage these systems rather than focus exclusively on conscious, analytical learning. It suggests the importance of experiential learning, apprenticeship models, and embodied knowledge acquisition. Approaches that work with, rather than against, our evolved learning mechanisms. That recognize the power of intuitive understanding alongside analytical reasoning. The revelation extends to our relationship with other species. If human cognition represents one expression of evolutionary processes that shaped all minds, then other species possess their own forms of consciousness, different but not necessarily less complex, specialized for their ecological niches. This recognition demands humility about our place in nature. We aren't the culmination of evolution, but one branch on a vast tree of consciousness. Our particular form of awareness represents not the only way of knowing, but one possibility among countless others. Perhaps most profoundly, the big reveal transforms our understanding of ourselves. If human intuition has roots stretching back 5 million years, if our consciousness emerges from systems shaped by our evolutionary history, then self-understanding requires acknowledging this ancient heritage. We are not the rational, autonomous individuals of Enlightenment philosophy. We are biological beings shaped by evolutionary forces. Our perceptions, preferences, and intuitions influenced by adaptations we neither chose nor consciously recognize. Yet this doesn't diminish but enriches our humanity. For in recognizing our evolutionary heritage, we gain something precious: perspective. We see ourselves as part of a vast, ongoing process, connected to all life through shared evolutionary history. Our consciousness not separate from nature, but nature become aware of itself. This perspective doesn't reduce human experience but expands it. We recognize ourselves as inheritors of knowledge accumulated across geological time, carriers of wisdom embedded in our neural architecture, expressions of a process far greater than our individual lives. The dawn of human instinct 5 million years ago represents not just a chapter in our evolutionary past, but the beginning of a cognitive journey that continues today, a journey in which we're now conscious participants, able to understand and potentially guide our ongoing development. For the first time in evolutionary history, a species can comprehend its own cognitive design, can recognize both the power and limitations of its intuitive systems, can develop tools to extend beyond these limitations, can consciously participate in its continued cognitive evolution. This represents an unprecedented transition from unconscious evolution to conscious self-development, a transition made possible by the integration of our intuitive systems with our capacity for abstract, symbolic thought, creating the possibility of genuine self-understanding. The ultimate revelation is that human instinct isn't finished evolving. Our cognitive architecture continues to develop through the interaction between biological and cultural inheritance, between genes and ideas, between evolved intuitions and created technologies. We stand at a unique moment in this process, able to look back across 5 million years of cognitive evolution, to recognize the forces that shaped our minds, and to consciously participate in determining what our minds might yet become. A responsibility and opportunity without precedent. The dawn of human instinct wasn't a moment but a process, one that began 5 million years ago and continues today. A process in which we are both products and participants, inheritors of ancient wisdom and creators of new possibilities, an extraordinary journey of consciousness becoming aware of itself. As we conclude our journey through the dawn of human instinct, we return to where we began, standing in that ancient East African landscape 5 million years ago, where our earliest ancestors took the first steps on an unprecedented cognitive path, a path that would eventually lead to us. Those first steps weren't dramatic. No sudden cognitive revolution, just subtle neural adaptations to changing environments, enhanced attention to movement at the periphery of vision, more sophisticated tracking of social relationships, slightly improved causal understanding, small changes with immense consequences. What makes this story so remarkable isn't its drama, but its continuity, the unbroken chain linking those ancient adaptations to your consciousness today. The way your mind still carries the imprints of challenges faced by countless ancestors across evolutionary time. This continuity offers both humility and wonder. Humility in recognizing that our vaunted rationality emerges from ancient intuitive foundations. Wonder in appreciating the extraordinary evolutionary journey that produced our particular form of consciousness. The open questions remain fascinating. How might our understanding of these ancient cognitive foundations help us address contemporary challenges? How might it guide the development of artificial intelligence or transform educational approaches? How might it shape our relationship with other species and our planet? Most intriguing of all, how might conscious understanding of our cognitive evolution influence its future trajectory? For the first time, we possess the capacity to comprehend the forces that shaped our minds, and potentially to direct these forces toward consciously chosen ends. This represents not the end of human cognitive evolution, but a new chapter, one in which we participate not just as products, but as co-creators, a responsibility that requires the deepest understanding of our cognitive heritage, of the dawn of human instinct 5 million years ago. As you carry this ancient wisdom within you, remember, your intuitions represent knowledge accumulated across evolutionary time. When you sense, feel, know without knowing how you know, you're accessing the collective wisdom of countless ancestors who survived to pass their genes to you. Subscribe to our channel for more journeys into humanity's deepest mysteries, where ancient wisdom meets modern discovery in the continuing story of what makes us human.